Well, hello everyone. Today we are going to focus our attention on the nucleus of the atom, looking at what we call isotopes. So if you'll get out your study guides and turn to uh, your isotopes, I think it is lesson 5. We'll go ahead and get started with that. All right, lesson 5, isotopes. All right, follow along in your study guides. Take some really good notes. Isotopes is a very important topic in chemistry, but it can also sometimes be a little confusing at times. So I would recommend you not only take great notes, but go back and review this video a couple of times. Okay, so let's get started. So remember that in lesson 3, we focused on the structure or the basic structure of the atom. We said that the nucleus of the atom is composed of neutrons and protons, and the electrons are outside of that nucleus in some sort of motion around the nucleus, and the electron is located in the electron shell or energy level as depicted by this diagram. So for this particular video that we're looking at today, or in our study guide, we are going to be focusing on the nucleus and specifically the protons and the neutrons and the numbers of protons and neutrons in that nucleus. All right. So let's first, as we get into isotopes, let's define what an isotope is in the first place. However, we do need to talk a little bit about protons and the importance and the meaning of the proton number. So the particular number of protons in the nucleus determines the identity of the atom. So what do we mean by that exactly? Well, each atom, as we've talked about before, element, has a particular name. Hydrogen is hydrogen, oxygen is oxygen, carbon is carbon. But really what determines the element and the reason why we identify an element as being carbon or an element being hydrogen is because of the number of protons in the nucleus of those particular atoms. For instance, hydrogen has 1 proton in the nucleus, oxygen has 8 protons in the nucleus, carbon has 6 protons in the nucleus. And because we look at any atom that has 6 protons, we are going to say, well, that's going to be a carbon atom or carbon element. Okay, if any atom or element has 1 proton in the nucleus, it's got to be hydrogen. If any atom or element contains 8 protons in the nucleus, it's got to be oxygen. Okay, so again, the number of protons in the nucleus identifies what type of element or atom we're looking at. If we alter the number of protons, we add 1 or we take away 1, it will completely change the identity of the atom. For instance, if you have a carbon atom, which again has 6 protons in it, and you add 1 more proton, and now it has 7 protons, it's no longer carbon, it now becomes a nitrogen atom. All right, so think about the identity of any atom based on the number of protons it has in the nucleus. Okay. By the way, as a note, if I change the electron number or the neutron number, it does not interfere with the identity of the atom. Okay. Protons are the only particle that determines the identity of an atom or an element. Okay? Electrons and neutrons we can mess with, we can change, we can add, we can subtract, and it will not change the identity of the element or atom as long as the proton number stays the same. Okay? I hope we've made that clear to you. All right, so let's go into the definition. Oh, before we get into the definition of isotopes, let's take a look at this example. So we have in your notes these three atoms. Beryllium, and if you look at your periodic table, the atomic number for beryllium happens to be 5. Okay, so therefore the atomic number gives us the number of protons, if you remember. So this is going to also equal the number of protons in our nucleus. All right, and all beryllium atoms must have 5 protons. So if you look at the nucleus here, often you can identify the particle by the correct number of protons. So in this case, let's see, the dark ones, 1, 2, 3, 4, 5. So it looks like the dark ones might be our proton number because we only have 1, 2, 3, 4 of the white ones. So in this case, we could say that the proton number here is these dark ones, and so that must mean the lighter ones here are the number of neutrons, okay, in that nucleus of beryllium. Now remember, I cannot alter this 5. If I alter the 5, I alter the identity of beryllium, okay? So fluorine, how many protons does fluorine have? If you look at the periodic table, if I look at my periodic table, it says that fluorine should have 9 protons because the atomic number is 9. So 9 protons in the nucleus. So you'd find which one. Let's see if the dark one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh. So the dark ones cannot be protons, but what about these lighter 1, 2, 3, 4, 5, 6, 7, 8, 9. So now in this case, these lighter ones here represent the protons, and the darker ones must represent the neutrons for this particular atom. And again, we cannot alter the 9. If we do, it's no longer fluorine. So what about carbon? Well, this one's going to be hard because if you look, 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. So they both have 6. And we know that the number of protons that carbon has, as we've mentioned earlier, is 6. 6 protons in the nucleus. The atomic number of carbon is 6. So how do we determine? Well, in this case, it's hard, okay? So we could say easily that the dark ones might represent the number of protons, and then the light ones are the number of neutrons, just because they're the same number in this case, okay? All right, but bottom line is what we're trying to get is that the atomic number of these elements that we find on the periodic table represent the number of protons, and it is the proton number that makes the identity of the atom what it is, okay, on that idea. All right, now we'll get into the definition of isotopes, okay? And then we'll look at some examples on what we mean by it, okay? So an isotope, by definition, are atoms of the same element. Atoms of the same element. So what we're saying here is that an element might have different atoms or different types of atoms, okay? So atoms of the same element that have the same number of protons, which should make sense, okay? Because those atoms, those protons identify the type of atom. So same number of protons, but they have different number of neutrons, which result in different mass numbers. Okay, so we'll look at what we mean by isotopes here. So make sure you have that definition down. All right, so what we're going to look at is some examples of isotopes. So we have hydrogen, and if we look closely, it looks like we have 3 different atoms of hydrogen. Now, hydrogen should have how many protons? Well, what's the atomic number of hydrogen? Look at your periodic table. It should say an atomic number of 1. So therefore, hydrogen has 1 proton in its nucleus. Now, is that the case for all 3 of these atoms? And it is. You have 1 proton. Remember, protons are positive charge. So you have 1 proton in the nucleus, another proton, and then another proton. Okay, so it looks like each of these hydrogen atoms have a proton. But notice that their neutron numbers, this would have to be the neutrons here, okay? These ones that are blank, the number of neutrons are different, okay? This first one here doesn't even have any neutrons whatsoever. The second one only has 1 neutron, and the third one has 2 neutrons, okay? Well, these 3 atoms are atoms of hydrogen. Now, how do we know they're atoms of hydrogen? Again, because they have 1 proton in the nucleus of these atoms. And since the proton identifies the atom, we must say that each one of these atoms is a hydrogen atom, okay? But what's different about these, sorry about that, what's different about these atoms is their number of neutrons. So because they have the same proton number, but different number of neutrons, we refer to these 3 different atoms as isotopes of hydrogen, okay? So they are isotopes. Okay, isotopes of the atom hydrogen, all right? Again, same number of protons, but different number of neutrons. Now, we don't care about the electrons. We are just focusing on the nucleus of the atom. Again, all we need to realize that the definition of an isotope is just simply saying that if atoms have the same proton number, but they differ in their neutrons, then they're going to be isotopes of the same element. Okay, so let's look at a second example, lithium. All right, now we have 2 atoms of lithium. First of all, let's make sure that they are lithium atoms. So what is the atomic number of lithium on your periodic table? Okay, if you said it's an atomic number of 3, you're right. So therefore, lithium has 3 protons in the nucleus of the atom. And that is the case here. We have 3 protons, 1, 2, 3. And in this atom, we have 1, 2, and 3. So we know that both these atoms are atoms of the element lithium. But are they isotopes? Well, do they have different number of neutrons? Well, this one has 1, 2, 3 neutrons, and the other one has 1, 2, 3, 4 neutrons. So they do have different numbers of neutrons. Because they have different numbers of neutrons, but the same number of protons, they must be isotopes of the same element. So they're different atoms, but they're both atoms of lithium because the number of the number of protons is 3. But they're different atoms because they have different neutron numbers, okay? Now, of course, that would result in a different mass, all right? The mass is defined by the total number of protons and neutrons in the nucleus. So if we look at this lithium, it has 1, 2, 3, 4, 5, 6. So we would say that it has a mass of 6. And so we'd say a mass And specifically, we call it a mass number. Mass number, okay, of 6. Well, what is the mass number of this atom? Well, we count 1, 2, 3, 4, 5, 6, 7. So this has a mass number of 7, okay? So lithium, it looks like, has 2 isotopes, defined again by their number of protons, which is 3, but they have different number of neutrons, which results in 2 different mass numbers, lithium 6 and lithium 7. Okay, hopefully that's clear. All right, so let's look at some isotopes of carbon. From this diagram, all we're looking at is the nuclei of carbon. The electrons are not represented. So we have one isotope of carbon here that has, of course, 6 protons in it, but it has 6 neutrons. This isotope of carbon has 6 protons, which it should because it is an isotope of carbon, but it has 7 neutrons, and the last one, 6 protons and 8 neutrons. So we can say that all 3 of these nuclei represent the element carbon, or are carbon atoms, because they have 6 protons each. But they are isotopes. All 3 are isotopes of the element carbon because they have different number of neutrons in their nucleuses. Now, if we add up these proton and neutron numbers, you will get a mass number of 12 here. This is the mass number. Okay. And for this one, 6 and 7 is 13. And for this one, 8 and 6 is 14. Okay, so the mass numbers of each one of these isotopes indicated right here. All right, now you will notice that you see 12, 13, and 14. And you'll see that the name of the element or atom, carbon, followed by a hyphen, and then 12. And that's typical on naming or identifying these particular isotopes. So we have carbon 12, carbon 13, and carbon 14. So carbon, or the element carbon, is made up of 3 different isotopes, carbon 12, 13, and 14. So this number here that's separated by the hyphen is known as the mass number, okay? And so we can name elements or atoms of an element by their mass number. So carbon 12, 13, and 14, okay? Now, these percentages that you see here represent the abundance, or how common these particular isotopes of carbon are found in nature. So we can say that about 98.9% of all carbon atoms are carbon 12. 1.1% of all carbon atoms are carbon 13, and less than 0.1% of carbon atoms are carbon 14. So carbon 14 atoms are the least abundant in nature, and carbon 12 is the most common carbon atoms that are found in nature. So we will talk more about the abundance of these isotopes at a later date this year. But just know that isotopes of the same element are not found in equal abundance in nature. Okay, so keep that in mind. Again, atoms of an element are not found in equal abundance in nature. These isotopes vary in their abundance, okay? So let's go back to the previous slide here, where we had our 2 atoms or elements of hydrogen and beryllium. Okay? And let's identify these by its mass number. Okay, so for the first one, because there's only one proton, and no neutrons, this first one is going to be identified as hydrogen with a hyphen and then a 1 representing hydrogen 1. The second one is going to be represented by need to spell that right. Hydrogen what? There's my hyphen. Hydrogen 2, 1, 2. Okay, the mass number is 2. And then this last one here is going to be represented by hydrogen, what? 3, 1, 2, 3. Okay, and so forth. Okay, and lithium, we got lithium what? Well, 1, 2, 3, 4, 5, 6. So this is lithium 6. So we'd actually put a hyphen and put 6. Okay, or in this one, it's 1, 2, 3, 4, 5, 6, 7. So we'd actually, here, we would actually have to put 7 here. Okay, so lithium 7 to represent this one there. Okay, so I hope this is making sense about what an isotope is, how we can identify an isotope by its having the same number of protons but different number of neutrons, and does result in a different mass number. Okay. All right, so let's move on here for a moment. Okay, we're almost done. To remind you, there are 118 elements in nature. And each one of these elements, all of them, represents a variation of isotopes, okay? So every single element has at least 2 different isotopes or 2 different atoms that make up that element, okay? So we need kind of a standard way to represent those isotopes symbolically for an element. So here's kind of the general idea of what we're looking at here. So this X here represents the symbol of some element, okay? And then up in the corner, always we're going to put the mass number, okay? And the mass number is represented by the number of protons, which is symbolized Z, okay? We use Z sometimes to symbolize the proton number or the atomic number, plus the number of neutrons, and that will give us A, which is represented the mass number. In the bottom left-hand corner is always the atomic number for that isotope or the number of protons. So for instance, with hydrogen, we can put hydrogen. It has, we know that has 1 proton, and then we saw that it had a mass of 1. Okay, so that would be hydrogen 1. Or we had another isotope, again with 1 proton, that was 2, hydrogen 2. And another one proton in hydrogen 3. Okay, so again, we put the mass number at the top, top left-hand corner, with the atomic number at the bottom left-hand corner. Okay, so let's look at those carbons, those 3 isotopes of carbon now. So we have what? Carbon with 6 protons and 6 neutrons, so we have carbon 12, and then we have carbon 13, and then finally the least abundant carbon 14. Again, we put the mass number up at the top left-hand corner and the atomic number at the bottom, okay? So that's, in this class especially, we're going to represent the isotopes of an element in this manner using this elemental symbol notation, okay? So get familiar with it really well. All right, last thing, we're just going to define a mass number again. The mass number is the total number of protons and neutrons in the nucleus of the atom. Okay, so again, we take the proton number in the nucleus, we take the neutron number in the nucleus, we add those together, and we get a total mass number. This should always result in a whole number. Okay, it should always be a whole number. There should be no fraction, because we don't have a fraction of a proton or a fraction of a neutron. All right. All right. So what I think we should do is go ahead and end our video here for today on isotopes. Again, I would strongly encourage you to go back and review your notes on isotopes really well. Might even want to re-watch this video. Make sure that you got notes down that you need to. Please come to class with questions about isotopes if you have them, and we will discuss them and see what we can do. Okay, so that is it for now. So we'll see you later. Have a good one.